Assalamu alaikum. Actually, I wanted to record with you some other topic, but I received a comment by a student today that sir, I face problem regarding quick return and non-quick return mechanism. So can you upload video for quick return and non-quick return mechanism by tomorrow? So I thought I would be helping if any student is facing some problem. So before proceeding towards the quick return and non-quick return mechanism video record, because that is the topic of dimensional synthesis, so I will be giving some brief descriptions and important uh, statements about the dimensional synthesis. So this is chapter number 3rd in the book of design of machinery by R.L. Norton, 6th edition. So dimensional synthesis, what is dimensional synthesis? The author has actually written here that the dimensional synthesis of a linkage is actually the determination of the proportions. Proportions means the sizes, you can say, or the lengths of the links necessary to accomplish the desired motion. It is necessary because we know that in the Grubler or the Kurzbach formula that only actually relates that actually only relates the number or count of the links to give a specific DOF. For example, the Grubler formula say that gives us a 1 DOF mechanism, but if we fabricate wrong dimensions or wrong sizes of the links, we will not be obtaining 1 DOF mechanism, because there may be the situation the links may be partially moving or they wouldn't be moving at all. So dimension thesis actually guarantees the required motion, because we first of all apply the Gruber formula and solve the problem to obtain a given DOF, for example 1 DOF or 2 DOF, and after that once the DOF is obtained depending upon the given count of a link. For example, there are 4 links and we obtain that 1 DOF is obtained for 4 links in a mechanism consisting of all revolute joints. So after that, to obtain the required sizes of the links so that the required motion or output is achieved, we will be performing or doing the dimensional synthesis. So synthesis is actually the process is actually by which the links dimensions are specified. So here in this chapter actually the synthesis process is actually graphically given, means with the help of pencil, scale and geometry box relevant material you can perform the dimensional synthesis, or can specify or can draw the links on a paper or some drawing sheet, and from there you can measure the sizes or proportions of the links. So article 3.2 is important, that states that the function path and motion generation. So there are 3 types of dimensional synthesis which are called function path and motion generation. So the definitions are written here. Briefly I will be reading them. That function generation is defined as the correlation of an input motion with an output motion in a mechanism. So actually in the function generation an input motion is actually mapped is actually mapped as the output motion. For example, the crank in a 4-bar mechanism, for example Grashof compliant mechanism is there, and the crank completes full 360-degree revolution, means crank is in pure rotation. In a similar manner, output is obtained at the rocker, and rocker motion is also actually pure rotation, or we can say a partial rotation, means oscillation about its grounded revolute. So in this way, same type of motion is actually mapped in a similar manner. So this is called the function generation. And similarly, the other type is path generation, in which actually a specific point on a link in which is in complex motion, for example the coupler link, and the motion of that point is actually controlled to obtain a specific path. For example, if we want to create some elliptical shape or any some important engineering curve, so we can actually define the location of the point on the coupler link, because the coupler link is in complex motion. So that point which will actually be describing the path, required path, so that is called the path generation process. So the third type is actually the motion generation, in which a complete link is actually moved from one given position to another given position. So further details are not to be covered at this stage. So we will be going directly toward the creation of the non-quick return mechanism first. So in article 3.4, the first actually topic is the position synthesis. So in the dimensional synthesis, first is the position synthesis. So at this stage we must also know the difference between synthesis, position synthesis, and position analysis. So remember that the position analysis mean actually that the sizes of the links have been once specified, then we give the input location, for example angular displacement for the crank, and depending upon or given the input angular displacement, we obtain or we snapshot or we can picturize the position of all the links on a paper or on some drawing sheet. So that is called position analysis. Position analysis can be made graphically or analytically using some algebraic relations, which is covered in chapter number 4, position analysis. Whereas the position synthesis is actually, that is the determination of the sizes or proportions or lengths of the links by specifying or drawing the position of the links, and that position which actually be giving the sizes of the links, means in the analysis the sizes have already been determined, whereas in the synthesis process the sizes are actually determined. So that is the first process before the analysis. So analysis is done after that, and before the analysis the synthesis process is done, by which the sizes of the links are determined depending upon the DOF of the mechanism, which is obtained using the Gruber formula. So This is the position synthesis. So position synthesis has further types. There are two position synthesis, and that actually states here that the two position synthesis subdivides into two categories. Rocker output means pure rotation, and the coupler output. So non-quick return mechanism and quick return mechanism both are actually the rocker output means pure rotation. So that is called the two position synthesis. And two position synthesis means actually we map the output link between two extreme position which are actually the limiting positions. So that is called the two position synthesis. And the size of the output link or rocker is actually given. So the method is actually covered in example 3-1, the rocker output two position with angular displacement. So example 3-1 actually describes the procedure for non-quick return mechanism. So here is written the procedure. I will not be reading the procedure, so I will just be explaining this diagram. So in the process of drawing this non-quick return, so actually the non-quick return mechanism actually states that as we can observe here that, for example, B1 and B2 are the two extreme positions of the rocker link. So what we actually do, that we picturize or place the rocker link at between two extremes, and B1 and B2 are the two extreme positions of the rocker link. And if we connect these two extreme positions of the rocker link and we extend this line, and the crank grounded revolute means this point, for example, is actually located on the line which is actually connecting the extremities of the rocker link, then we will actually be obtaining the non-quick return mechanism. Means this is actually the throw or the stroke of the rocker. This curve is actually the angle subtended by this rocker link at the grounded revolute O4. That is actually the throw or stroke, angular stroke of the rocker. Similarly, in the crank slider chain mechanism, the slider throw is actually the linear throw or linear stroke, whereas in the case of rocker link the stroke is actually angular stroke or angular throw. So that means that if the crank grounded revolute is located on the line which is actually connecting the two extreme positions of the rocker, so if the crank grounded revolute is on that line, then the output of the rocker will be non-quick return, means the rocker will be moving with constant velocity in the forward and the return stroke. For example, rocker goes from B1 position to B2, it will be taking the same time as it will be taking the time from coming from the position B2 towards B1. So in the to and fro or back and forth motion of the rocker between the two extremes will be uniform velocity. So whereas in the case of quick return, what happens that the crank moves with constant angular velocity, but the structure is actually so fabricated that the motion of the rocker is not constant in the forward and the reverse stroke. Maybe the rocker is actually moving with greater velocity in the return stroke than the forward or working stroke. So that is the reason. And if we want to design the quick return, that I will be covering later in the video, that this crank grounded revolute will not be located on the line connecting the extremities of this rocker link. So that will be offset from this line, either in this direction or in this direction. So that is actually the principle. So how it will be done, I will just briefly be describing the procedure that we will be drawing. For example, we will be specifying or assuming the size of the rocker link. So the first will be that we will be assuming the size of the rocker. So I can show work here. For example, any size of the rocker can be assumed. Rocker is usually denoted by the scalar length letter C. So I can type here, for example, just small letter C. So for example, its length is 5 centimeter or 5 inches. Any suitable value that can be assumed to start the position synthesis process. So once for example at this stage, I will be assuming the dimensions in centimeter or millimeters. So I will be taking the dimension of the rocker, for example 5 centimeter. So if after completing one synthesis process, if the Grashof law is not satisfied, if the Grashof law is not satisfied, means S plus L is not less than P plus Q, then we will be changing the size of the rocker or link, means the length of the rocker can be changed. So we will again be performing the synthesis process until the Grashof law is satisfied. So what I can do, for example, we can insert similarly go into the shapes area and draw a line here. So for example, this is the first extreme of the rocker position. So depending upon the length of this line, first specify the size or length of this line. So use this linear scale and here we can specify the size of the, for example, here we can observe here that in this way. Here, as we can observe here, now change the size of the rocker like this. For example, here as we can observe, 5 centimeter length for this rocker link has been specified using this linear scale, and this position of the rocker has been created. Now we can, for example, at this stage label the grounded revolute for the rocker, and which is actually insert text box, and in a similar manner I can type here. This point is actually O4 because the rocker is actually the fourth link according to the book of design of machinery. So change it into subscript. So again go into shape fill, no fill, and shape outlines to no outlines. So in this way this rocker grounded revolute has been set out. Remember that at any random orientation the rocker link can be set out. That will not make an issue. After that we will also be assuming its throw. So for example, we can insert symbol here, for example theta 4, theta subscript 4, because 4 is actually the subscript or digit used for the rocker output or rocker link in this book. So for example, the throw of the rocker means this net angle between these two extremes B1 and B2 is actually the net throw of the rocker link, this theta 4, that can be assumed any suitable value less than 180 degrees, remember. So usually up to 120 or 130 degrees maximum preferably. So I can for example assume 100 degrees. For example, I can assume 100 degrees is the total throw. So that means 50 degree on either side of the rocker mid position. So between the two extremes there will be 100 degrees. So any suitable value can be actually assumed, so that doesn't make issue. So if by assuming one throw the Grashof law is not satisfied after performing or completing the dimensional synthesis, so the size of the rocker or the length of the rocker will be changed. For example, that can be changed for other than 5 centimeter, that may be increased or decreased in this way. So we can change the length of the rocker. So this is the initial assumption. So the rocker throw is actually 100 degrees here. So that means we will be taking the protector like this, and we will be placing the protector, for example for example here this is the. So in this way actually I am making you understand that with the help of physical protectors you will be measuring the angles like this. this zero line center of the protector should be exactly matching here. So now we can observe that, for example, this is so as we can observe here, this is 100 degrees. So that means we can insert, and for example, another line, and we can randomly draw at this location here exactly the same size as the original rocker link. So we can again set the size with the help of this linear scale and just move it here. So make it exactly 5 centimeter. So that means the positions B1 and B2 has been set out, as we can observe here, that we have considered the upper graduation means 10, 20, 30, 40, 50 and 90, and this is 100 degree. So in this way, now move this linear scale and protector out from this position, and again we can similarly copy this label and just paste and define the position. For example, this is position B1, and as we can observe towards right, that is position B1, and similarly if we can just copy it and paste it and then can move it. So this is the position B2. So at any random location that doesn't require or necessary that the mid position of this rocker be vertical, that is not necessary. At any random location these rocker positions can be drawn, and the angle between that can also be specified using this arc. Here you can use up or down arrows very carefully. So in this way, so we can observe this theta 400 degrees has been specified. So after that, actually what will be the procedure, that we will be assuming the size of the coupler link or connecting rod, and we will be describing some arc of the assumed size of the coupler or connecting rod, and we will be describing an arc by assuming first the center at B1 and second time the center at B2. So I will be performing here the procedure. So now we can assume any suitable size of the rocker link. So first of all, as we have specified these extremes of the rocker link, so we actually first draw the line that actually connects these 2 points, and we can extend it randomly like this, in this way, remember. So this is quite random. So I have drawn the line connecting B1 and B2, which are actually the extremes of the this rocker link. So after that, what we will be doing, that we will be opening the compass by assuming some suitable size of the coupler or connecting rod link. So here we can assume any suitable size. For example, coupler link is actually united by the scalar length B. So for example, B can be assumed any value, or we can draw a random radius. So for example, I can say that B is equal to, for example, 10 centimeter, just it is assumed. So what we will be doing, that we will be drawing an arc or a circle with a center at B2 and B1, and we will be describing two arcs these that will be intersecting this line, which is actually connecting B1 and B2. So what we can do, we can, for example, first of all bring the protector here like this, and similarly we can place it a 0 line, 0 and 180 line that must be overlapping. Sorry, we can use arrows. Here like this, so it is exactly almost exactly on the line. So as sorry, 0 line is here, so like this. Again, here like this, it is on the 0 line. So now we can actually resize it according to 10 centimeter. Again, also we can place this scale to measure 10 centimeter. Remember that this is assumed length of the connecting rod, and that may be changed if the Grashof law is not satisfied after that. So here we can observe that 10 centimeter will be here, like this. So now we can again resize and again so again that requires further extension 10 centimeter, because so it is actually taking time in this Microsoft Word, whereas if we will be doing work on paper and physical protectors, so that will not be taking much time. So as we can observe here that about 10-degree dimension has been obtained, as we can observe here that this protector radius is at 0-degree line and here is 10, so 10 centimeter length is actually obtained. So in this way, now what we will be doing, that we will be going into shapes, and similarly we can just draw after that we can go into shape and shape fill into no fill. So here like this, so in this way, as we can observe that the required circle has been drawn. Now we can resize or then move the protector out, leaving the drawn circle, and we can also move this linear scale out. So also change this circle into some dashed pattern or center line, sorry, here dashed pattern here like this, because that is actually just a reference circle. So in a similar manner we can just copy this circle, and for example, to move this circle, we can also insert some as a reference. We can draw here this just circle to indicate its center, and now we can just, for example, we can copy it by pressing Ctrl and this, and now we can just copy it, and now we can for example paste it here. So now we will be using the up and down arrows like this. Or we can just drag this whole system here at this location very carefully. So now as we can observe that this is the second circle that has been described. So these are two arcs that have been drawn at B1 and B2. In Microsoft Word I have to draw this complete circle, but while you will be working on A4 size pages or drawing sheet, you will only be drawing suitable arcs as required. So now as it can be observed that two extremes have been drawn. So remember that we can respectively label these extremes of connecting rod or crank, and just similarly this point we can say this will be A1, this will be the extreme of the crank when the rocker will be at the right extreme B1, and similarly if we can copy this extreme and label, and we can change it here to A2, A subscript 2. This is the other extreme of the crank. And what will now we be doing, that here we will be describing the same size circle at the mid location of the rocker. So this line which it has shown, this is actually the angular bisector of this total throw of the rocker. This is the total throw of the rocker, and this line is actually the angle bisector, mean this line is actually dividing the total throw of the rocker into two equal portions. So that line can be physically or practically drawn on the A4 size paper such that we will be opening the compass by some random radius which is greater than half the throw or half the distance between B1 and B2. So any random radius which is greater than half the throw of this rocker. So we will be describing, we can first of all we can draw one arc here and of the same radius arc here, and after that we will be taking the center B1, first B2 and B1, or alternatively in any order, first B1 and second time B2, and we will be describing the same radius. We will not be changing those radii once have been specified. So we will be describing these two arcs here, and after that their intersection will be connected with each other, and that line will be extended towards this pivot. So in this way the center or mid position of the throw will be achieved, and this line will be intersecting this straight line at this point. So we will be describing the third arc that will be actually giving this point O, that will be the crank grounded revolute that on that line, and the radius of the arc will be the same as equal to the connecting rod. So here what we will be doing that at this stage, because I have protector, so that will make work easier. So what we can do that we can simply as we can observe here that for example place this protector like this, and as we can observe here 0 1 2, this is 100-degree throw here if we are carefully observing the inner protector markings 10 20 30 40, and this is 100 degrees. So that means this is the 50-degree, this is the central or mid position of the rocker. So I can randomly draw from this point O4 to this at 50-degree line, random reference line, and again change its outline to dotted line. So this is just a reference line. So now the protector can be moved out, and again the procedure is same, that for example we will be selecting these two circles, and now we will be selecting, and now we will be copying, and then we will be repasting. So that has been repasted here, and now what we can do that in this way that can be placed here. So as we can observe, this is the point O2. So just copy this label and here change it to capital O subscript 2. So in this way crank grounded revolute has been specified. So after that we will be this crank grounded revolute will be connected with this O4. So that means, for example, this is actually the grounded O2 O4. This is actually the grounded link, or link D. So its scalar length is D. So I can, for example, just copy this label, and now I can mention the scalar length of all the links. This is actually just, you can type it, this is small d, and in a similar manner, if we can just copy and paste and just change this label, so this is actually C, and C and D have been specified, and the crank length O2, crank length small letter a, that will be actually the distance from O2 to A2 or O2 to A1. So what I can do, that I can describe here some random circle if required, or that doesn't need, because the circle will be drawn with the help of protractor, so that is unrequired. So I can just mention here the size of the crank. So copy this label here, this is the length, this is A, this is the crank, and so sorry, instead of showing it here, we can show it here. So A and B, and B is actually this total length that I can show here, just like this. For example, O2 to this midpoint, or from A1 to B1 or A2 to B2 is actually the length of the connecting rod. So like this, for example, this distance is actually the length of B, which is actually the connecting rod. So just copy this label and paste it here, and just move it here, that this is equal to B. Now we will be, so all four links have been specified, but now we will be measuring the dimensions of the links A, B and D. So we will be measuring with the help of this linear scale. So bring the linear scale, first of all measure the crank, and here we can observe that this crank very carefully, as we can observe here, this is this is 1 2 3, and we can, for example, zoom in like this for better visualization. So as we can observe here, this is about 3.9 9 for example, so 3.9 centimeter. So I can mention here that a is equal to 9 uh, sorry is 3.9 centimeter. 3.9, a is equal to 3.9 centimeter. And now in a similar manner, measure the length b. B was already specified, that we can again verify that this is equal to 10 centimeter. So I can also mention here that I can also mention here so I can also mention here that O2 A2 is equal to O2 A1, a subscript 1. So these are actually all equal to the crank length. Sorry, uh, in this way. So in a similar manner, we can observe that this length is actually 10 centimeter, as can be verified. So now measure the length d. So move the linear scale parallel to it here. So here so as we can observe here that this is equal to here 10, and it is about we can just zoom for better clarity. So as we can observe here that is equal to move this label O4 a bit aside. So as 10.5 centimeter. So here mention that B is equal this is D is equal to 10.5 centimeter. So now apply the Grashof law, that S plus L must be less than P plus q. So as we can observe here that the smallest link, as we can observe here, 3.9, and plus the largest link here that came, that is actually 10.5 centimeter, and their sum is equal to, we can use this calculator, 3.9 plus 10.5, so that is 14.4. so 14.4. and in a similar manner you can mention here that the P plus Q is actually 10 plus the rocker length was 5, so that is equal to 15. So that means 14.4 is sufficiently less than 15, so that means S plus L is less than P plus Q. So Grashof law has been satisfied in this way. So this is the procedure for completing the diagram for non-quick return mechanism. So in this way uh, so in this way non-quick return has been completed. After that, if we want we can, as we observe that the crash of law has been satisfied. If we want, then we can just like in this figure, we can sketch these links. So according to these dimensions, when you will be fabricating this mechanism, so it will be giving 100-degree throw between these two extremes, and these will be the dimensions of the links. So 100-degree will be throw. So in this way, non-quick return mechanism has been explained. So using the same procedure, you can draw this dimensional synthesis for this non-quick return mechanism on A4 size or drawing sheet. Uh, so if you have any question, you can fairly ask. So I will be recording another video for the quick return mechanism, so that this video is not made lengthy. So thank you and assalamu alaikum.